Okay, let's continue with the discussion of solid propellant modeling. Let's look at some basics first. I just want to remind that we are looking at AP HTPB composite propellants and a model to predict the steady burn rate and the burn rate of these propellants when subjected to pressure perturbations. Let's start from some fundamentals. Most of what constitutes a composite propellant is AP. It's 68% in the case of aluminized propellants, it's up to 85-86% in non-aluminized propellants. So AP shows the following burn rate behavior. AP starts burning only at 20 atmospheres. Ammonium perchlorate can undergo self-sustained deflagration only starting from 20 atmospheres. This is of course true for pure AP. With impurities this limit can get shifted a little bit, but the important thing is that whatever be the limit of pressure, when it starts burning at around 3.3 millimeters per second, okay, and then at burn rate, the AP raised to N for AP is A is 3.3 millimeters per second at 20 atmospheres, the N value is 0.77, okay. This is characteristic of deflagration that is controlled by a premixed flame, okay. Remember that when the index is close to 1, the behavior is controlled by premixed flames. We will formally see this a little later, but index is close to 1 when it is controlled by a premixed flame, and lower index usually means there is effect of diffusion, effect of lateral diffusion. So at the reason why AP starts burning at only 20 atmospheres is because the surface temperature that is required for AP to undergo self-sustained deflagration should be equal to at least the melting temperature of AP. Unless it melts, it cannot undergo exothermic decomposition, and if it does not undergo exothermic decomposition, it cannot undergo self-sustained deflagration, okay. So the low pressure deflagration limit, which is the LPDL of AP, is 20 atmospheres. Because it is only at 20 atmospheres, the surface reaches the melting temperature, which is approximately 870 kelvins, okay. So AP is the principal constituent of composite propellants. 65 to 88% of all composite of the mass is AP, and therefore its behavior plays a significant role in determining the burn rate of the propellants, okay. So this is first thing. The next limit which is important to understand is what is called the homogeneous limit. AP HTPB propellants are in general heterogeneous composite propellants, but imagine that the heterogeneity results from the fact that AP particles of variety of sizes are used. You have large particles and you have small particles, and in zones which have large particles the AP concentration is higher, and in zones where small AP particles are used the fuel concentration is higher. But now imagine that you use only very fine AP particles. As to how fine it should be will be precisely defined later, but let us say you use a uniform AP particle size and all AP particle size are very small, okay. If you assume that you are working with, let us say, 1 micron AP particle or 5 micron AP particle distributed in the binder matrix, okay, then everywhere in the propellant the oxidizer to fuel distribution is roughly the same, okay. So this is the homogeneous limit of a heterogeneous propellant. What you have essentially done is you started with a heterogeneous propellant, sort of broken down, imagine breaking down AP into very fine sizes and distributing it uniformly. A heterogeneous propellant will become a homogeneous propellant in this limit, yeah. It is an actual propellant.
So we have 1 to 7 micron size.
Correct, yeah. So when you do this, what you end up with is a propellant like this, which has 82% AP of very fine sizes, 1 to 7 micron. The rest is HTPB. This is the homogeneous limit of a heterogeneous propellant, and in this limit the burn rate is controlled again by a premixed flame. Since there are no heterogeneity in the condensed phase, the flame also will be a homogeneous premix flame without any variations of the kind that we saw in the picture in the CFD simulation for an actual propellant. So when you homogenize the entire AP with the binder, the flame in the gas phase will also become a homogeneous premixed flame. Okay. So in these two limits, the burn rate behavior is controlled by a premix flame and therefore the index is close to 1. Okay. And this is also the limit that this is the limiting burn rate, because the homogeneous limit is where you can get the maximum possible burn rate from AP HTPB composition. Effect of lateral diffusion, we have already discussed this in some detail. So when you are neither at the AP limit nor at the homogeneous limit, in reality you are somewhere in between. You have particles of variety of sizes sitting inside a matrix of HTPB, and therefore you have local pockets giving off AP decomposition products surrounded by pockets of fuel rich conditions giving off fuel vapors, and the oxidizer is trying to diffuse laterally into the fuel is trying to diffuse laterally into the oxidizer, and depending on the distance that it can laterally move before it starts reacting, the flame structure will be determined by the conditions of the extent of lateral diffusion. Okay. So what is the effect of lateral diffusion? The effect of lateral diffusion is, as can be seen from the burn rate data for several propellants that are shown in this plot, is to bring down the index from close to 1 to about a minimum of 0.43. So the limits, at the limits AP burns at 0.77, at the homogeneous limit it burns with an index of 0.82. When you add particles of disparate sizes or bimodal as it is called, you have two modes of distribution that are added. Because of the effect of lateral diffusion, there are zones which are controlled by premix flames, there are zones that are controlled by non-premix flames, and therefore the index comes down from 0.82 or about 0.8 to as low as 0.43. Okay. So burn rate behavior of multi-model AP HTPB propellants is boxed between the two well established premix limits. I am referring to the AP and the homogeneous limit. Influence of lateral diffusion increases with decrease in AP particle size. We have seen this is equivalent of reducing the diameter of the ethylene jet. Okay, that is the simplest way to remember this. So the extent of or the influence of lateral diffusion will be significant when the diameter is smaller. Okay, when the diameter becomes comparable to the distance that it can move in the lateral direction, and the influence of lateral diffusion will decrease with increase in pressure. Why is that? Because the reaction rate increases with pressure, and therefore the distance that the oxidizer and fuel can move laterally before it starts reacting is smaller. Okay. Therefore this reduces the slope of multi-model AP propellants as compared to premix limits. The last point also means the following: for the same composition, the influence of lateral diffusion is higher at lower pressures and lower at higher pressures. At lower pressures, reaction rates are lower, and therefore the extent of lateral diffusion is higher. Therefore the propellant, for example SD319 that you see here, is closer to the homogeneous limit at lower pressures. When the pressure increases, the extent of lateral diffusion decreases and it becomes controlled by other factors, and therefore the increase in burn rate because of lateral diffusion is not as high at higher pressures as it is at lower pressure. Therefore the slope comes down. That is the reason the slope comes down. Okay. So if I have to summarize it, what I would say is, when there are several particle sizes, the behavior is close to the homogeneous limit at lower pressure and the behavior is close to AP limit at higher pressures. Okay. So the slope comes down. Okay. Now that is only the cases that we saw are only with AP and HTPB. Of course there are several other additives that are used. So what can happen with several other additives is propellants with low AP loading, less than 80%, and or containing special additives like strontium carbonate, oxamide, etc., can burn slower than AP beyond certain pressures, okay, within the operating range. One example is shown here. This is the COM1 composition, which crosses over and burns slower than AP burn rate at pressures as low as 50 atmospheres. and recall that diffusion effect decreases with pressure, hence fraction of energy available for binder decomposition also decreases with pressure, and therefore low AP loading and additives like strontium carbonate, oxamide can exacerbate this effect of heat flux coming to the surface of the propellant. Okay, it can reduce the heat flux coming to the surface of the propellant. In fact, increase in pressure reduces the heat flux coming to the binder, and in adding strontium carbonate can make it worse. Of course, these are all not serious issues at high solid loading of AP, but at moderate or low solid loading of AP these effects can be significant. So the broad question is, can the variety of behavior that we just saw be predicted using a theory? And yes, and there are three elements to the theory. One is the statistical representation of the complex heterogeneous propellant. You have a wide variation in the oxidizer to fuel ratio inside the composite solid propellant, therefore you need some statistical way of representing what the average behavior is. That is the first part. The second part is parameter estimation. This is the critical part in propellant modeling because the processes are so complex, especially in the presence of additives and other ingredients, that it is not very easy to fix parameters for various processes that happen in the condensed phase, surface and the gas phase. Okay, and it is also important that we do not introduce too many parameters. See, if you have too many parameters which we can arbitrarily change, then there is no, we cannot claim that the results are predictions. Okay, in fact, with 2 to 3 adjustable constants you can explain away any burn rate variation. The idea is to not have any adjustable constants and make predictions. Okay, so the second part is the important part for parameter estimation, and it is done using the well established premixed limits. The third is a burn rate submodel for individual elements in the statistical representation. It will become clear what I am referring to in a few moments. Okay. So let us look at the geometry part first. The serial burning approach is used here. That is, what it means is that a multi-model AP propellant is statistically represented as a line consisting of binder matrix coated AP particles of various sizes. The cross section of a typical propellant will look like this, and this is converted into a statistical representation of the following kind. Okay, where imagine a large number of random lines drawn through the propellant. Okay, and the propellant, such lines cut through particles of different sizes and binder matrix, and then you can calculate what is the intersection of such lines with particles of different sizes for a large number of random lines, collect that data, and then when you average it, then you have what is called a statistical particle path. Okay, and the way the binder is distributed is by assuming that the binder coats particles, AP particles on a statistical particle path with constant thickness. Okay, so such a line, in fact it may sound very complicated, but the simple way of saying it is, if you draw a random line through a propellant of this kind, the probability that it intersects a particle of size d is proportional to the volume fraction of that particle. Imagine a box containing particles of different sizes. The question that is being asked is that if you draw a random line through that box, the probability, what is the probability that it will intersect a particle of certain size? The answer to that question is that that probability is equal to the volume occupied by the particle of that size. Okay. So the line fraction, as this is called, the fraction of the length of such a statistical line occupied by particle of size d is proportional to the volume fraction of di, of particles of size di, and the binder matrix is distributed by assuming that it coats each particle with constant thickness. So the binder matrix coating AP particles is a homogeneous mixture of fine AP and HTPB. What fine AP is, I will describe in describe a little later. Okay. So the binder matrix is assumed to coat remaining AP particles with uniform thickness, which you can calculate by simply equating the volume of the binder matrix, which is this mass fraction of HTPB by density of HTPB plus whatever AP is there in the binder matrix to the volume of this thickness surrounding the AP particle. A sphere surrounded by a binder matrix coating of size TB will have a volume which is pi by 6 d plus TB cube minus pi by 6 d cube. I think let me maybe write this. What I am trying to say is that you have, this is important because it later is used for calculating the oxidizer to fuel ratio and extinction. So you have AP of size Di, okay, and the thickness of the coating is TB. So the volume of binder matrix is equal to pi by 6 di plus 2 TB cube, these are assumed to be spherical particles, minus pi by 6 dA cube. Okay. This is the volume of the binder matrix over one particle. Okay. Now there are a large number of particles. So the number of particles of size Di is equal to the mass fraction of that size divided by the mass of one particle, which is the density of AP into the volume of one particle. Okay. Therefore, the total volume of binder matrix for particle size Di is the mass fraction of that size divided by, this is the number of particles, multiplied by this quantity, which is the volume occupied by one particle. Okay. Now you sum this over particles of all sizes, you will get the total volume of the binder matrix, correct. This is for one size. Without the summation, it is the binder volume of the binder matrix around one particle of size Di. When you multiply it by the number of particles of size Di, you get volume for that particle size, then sum over all the sizes. This is the total volume of the binder matrix coating all particles with uniform thickness. Okay. And the total available binder matrix, the available binder matrix is volume is the mass fraction of HTPB divided by the density of HTPB plus mass fraction of fine AP. As to what this is, I will explain. Fine plus extinct, both I will explain later, divided by the density of AP. So this is the total volume that needs to be coated. This will be the volume if it is coated with thickness TB. By equating these two, you can get TB equation. Okay. Is it clear? Okay, small. You will see exactly the whatever I have written at the bottom of this page, you will see it in the slide also. Okay, what you see here is exactly that. Of course, the pi by 6 has been cancelled out and the expression has been simplified a little bit, but essentially what is there on the left is the total volume of the available binder matrix. What is on the right is the volume if it is coated with a thickness Tb. Okay, so using this equation you can get an estimate for the binder thickness. Okay. And the line fraction occupied by particle of size di, which I imagine a random line going through a propellant pack, the probability of intersection is proportional to the volume fraction. So the line fraction of size di is proportional to the volume fraction of di, and that is what is used here to calculate. If you imagine a line of unit size, what fraction of it will be occupied by a particle of size di is calculated using this formula and corrected for the binder thickness. Okay. The calculated value is shown for a representative propellant here called SD322 from Miller 1982. Okay. So what we have done using this procedure is that we had a certain random distribution of AP particles of different sizes in the propellant. It has been now converted into a averaged line containing particles of various sizes proportional to their representation in the actual propellant, and the fuel has also been distributed in a certain fashion around these particles. Okay. Now moving on from here, the propellant burn rate is simply calculated as the length of this line divided by the time it takes for such a line to burn. Okay. And the time for this line to burn will be the sum of the times for each one of these particles to burn. So the burn rate of the propellant is the length of the statistically averaged path divided by the time. The length is L and the time is sum of time for particle of size di to burn. Okay, so you have a small particle, several small particles, you have a large particle and some small particles. Okay, so the burn rate is the time it takes for this particle to burn is the diameter of that particle. I'm sorry. The time that is required for this entire batch of particles to burn is the length occupied by that particle divided by the burn rate of that particle. The time that is required for this batch of particles to burn is the length occupied by this particle divided by the burn rate of this particle. So this will become sum over Li over R dot I. Okay. L is arbitrary, I can take L as 1, a unit line, and therefore R dot is sum over I So this is how the burn rate is calculated. Li is known from the geometry of the propellant. R dot I is yet to be calculated. Okay. This is the basic idea of calculating the propellant burn rate. We converted certain random distribution into this, okay, and from there we can calculate the burn rate of the propellant. Again, you see the formula here, it is the same formula, sum over all particles, Li over R dot I inverse. Now, having calculated the statistical particle path, we know how much AP is surrounded by how much of binder, and therefore we can calculate the local distribution of oxidizer to fuel ratio. And the oxidizer to fuel ratio distribution in a heterogeneous propellant, in a typical heterogeneous propellant is like what it is shown here in this plot. What is on the x-axis is the diameter of the AP particle, and what is on the y-axis is the percentage AP in each one of those particles, okay. It can also be expressed as oxidizer to fuel ratio. The important thing take away from this is same as what I mentioned earlier, pockets containing smaller AP particles are fuel rich, okay, and larger AP particles are oxidizer rich. This is the intuitive conclusion we came to by looking at the cross section of the propellant pack, and that conclusion is borne out by the calculations also. 88% is where around 88% is where AP HTPB is stoichiometric and has maximum flame temperature. Anything above that line is AP rich, anything below is fuel rich. What I want you to notice again is that larger particles are AP rich, smaller particles are fuel rich, okay. And the flame temperature reaches a peak around 88% AP and it is decreases on both the sides. On the right side it approaches the AP monopropellant limit, okay. So composition of binder matrix and binder thickness is used to calculate the oxidizer to fuel ratio. For a typical state of the art propellant, percentage AP distribution varies from as low as 55% here as you can see to as high as 99% for larger particles, okay. Stoichiometry is around 88%, and any theory that is developed to predict the burn rate of the propellant should account for this heterogeneity in distribution of oxidizer and fuel.